Hello everyone and welcome to another IB Physics video. Today we will be going over the answers for paper 1, Timezone 1 of May 2022. So let's get started. In this first question it says the intensity of a wave can be defined as the energy per unit area per unit time. What is the unit of intensity expressed in fundamental SI units? So first let's go over the units for energy. Energy would be, of course, represented in joules. Now the fact that it's per unit area means you have to divide this by the units per area. Area is in meters squared. And then you also have to divide it by the unit of time, which is going to be seconds. So we have to reduce the joules into fundamental units. Joules is force times distance, so it will be newtons times meters squared times seconds. So this will cancel out. Newtons are going to be kilograms meters per second squared. Meters seconds. And again, the meters cancel out. And we're left with only kilograms and seconds to the power of 3, which means the answer to this question must be D. For question number 2, it says the magnitude of the resultant of two forces acting on the body is 12 newtons. Which pair of forces acting on the body can combine to produce this resultant? So basically they're asking if you have a force 1, like so, and a force 2, would it be able to produce this force? Well, if you have two forces, the maximum value of the resultant would be when both of them are in the same direction. And the minimum value would be when one of them is in one direction, but the other one is in the opposite direction. And that way, the resultant would be bigger when they're in the same direction and minimum when they're opposite directions. So you have option A, 1 newtons and 2 newtons. The maximum would be 3 newtons if they're in the same direction, which means you would not be able to get 12 newtons. In option B, it's 1 and 14. 1 plus 14 is 15, which is big enough to get 12, but if they're opposite directions, it would be 14 minus 1, which is 13 minimum. You will not be able to get 12 newtons. In option C, 5 plus 6 is maximum of 11, so you will not be able to get 12. And option D, 6 plus 7 will give you a maximum of 13. And 7 minus 6 will give you a minimum of 1. 12 is between the maximum and minimum, so the answer should be D. In question 3, it says the uncertainty in reading a laboratory thermometer is 0.5 degrees Celsius. The temperature of a liquid falls from 20 degrees Celsius to 10 degrees Celsius as measured by a thermometer. What is the percentage uncertainty in the change in the temperature? In order to get the change in the temperature, we have to get the final temperature minus the initial temperature. And of course, 20 minus 10 is just 10 degrees Celsius. But if you have addition or subtraction, the absolute uncertainties add up. So in this case, the uncertainty would be 0.5 plus 0.5, which is plus or minus 1 degree Celsius. The percentage of that, of the total, would be 1 divided by 10, which is 10%. The answer should be C or D. In question number 4, it says, a block moving with initial speed v is brought to rest after traveling distance d by a frictional force of F. The second identical block moving with initial speed u is brought to rest in the same distance d by a frictional force of F over 2. What is this initial speed u? So first, when you have forces and distances, you can get the work done. And by getting the work done, you will be able to get the kinetic energy of that object. So initially, when it says it travels a distance d with a force of F, we know that the work would be F times d, which would be equal to the kinetic energy. In the second instance, it's the same distance d, but it's 1/2 the force. So it's 1/2 the force, F, times the same distance d, which means you would get 1/2 the kinetic energy. And because the kinetic energy is proportional to the velocity squared, if you have 1/2 the kinetic energy, you will not get 1/2 the velocity. You will get 1 over the square root of 2 of that velocity. So when it becomes squared, you get 1/2 the kinetic energy. Therefore, the answer to this must be B. In question number 5, it says, a stone is kicked horizontally at a speed of 1.5 meters per second from the edge of the cliff on one of Jupiter's moons. It hits the ground 2 seconds later. The height of the cliff is 4 meters and air resistance is negligible. What is the magnitude of the displacement of the stone? So, first, if you just follow the path, it will go something like this. Parabolic path. It goes down by 4 meters. And we know that if the horizontal speed was 1.5 meters, this horizontal speed will not change over the 2 seconds. So this horizontal distance is just 1.5 times 2, which is 3 meters. Now finally, the displacement is this vector here. How much it traveled from here to here. This is just a right triangle. And in fact, it's a special triangle. It's a 4, 3, 5 triangle. Otherwise, you get this by getting the square roots of 4 squared plus 3 squared, which is the square root of 16 plus 9, which is square root of 25, and it's still 5 meters. The answer should be B. Question number 6. It says 2 masses, M1 and M2, are connected by a string over a frictionless pulley of negligible mass. The masses are released from rest. Air resistance is negligible. Mass M2 accelerates downwards at g/2, which is basically half the gravitational acceleration of Earth. And it asks you for what is the ratio of M1 to M2. So first of all, we have gravitational force on one side. We call this M2 times g. Gravitational force on this side, which is M1 times g. Of course, mass 2 is heavier. So when you get to net force, it would be equal to the mass 2 times g minus M1 times g. Because they're in opposite directions, this mass M2 tries to pull it to this side, and mass M1 tries to pull it to the opposite side. Next, if you want the acceleration would be equal to the net force divided by the total mass. In this case, net force is g, and let's just factor this out. M2 minus M1, and divided by the total mass, which is M2 plus M1. Finally, you know that this acceleration should be 1/2 of g. Using this equation here, we just cross multiply. We get M2 plus M1 is equal to 2 M2 minus 2 M1. The g's of course cancel out on both sides. And that gives you 3m1 is equal to m2, m1 over m2 is 1/3. Therefore, the answer should be A. Question number 7. A book is at rest on the table. One of the forces acting on the book is its weight. What is the other force that completes the force pair according to Newton's third law of motion? Remember, Newton's third law says for every force there's an equal and opposite force. And the easy way to get this is you write down the sentence. What is the force of the weight on the book, right? Well, this is the force of gravity of the earth on the book. If you want to get the opposite force of this, you just switch earth and book. You write the same sentence, it would be the force of gravity of the book on the earth. If you look at the options, this is equivalent to A, the pull of the book on the earth. On question number 8, it says a cart travels from rest along a horizontal surface with a constant acceleration. What is the variation of the kinetic energy E sub k of the cart with its distance as traveled? Air resistance is negligible. So let's look at the options that we have. We have kinetic energy in the y-axis and displacement in the x-axis. Okay. We have to have an equation of kinetic energy using the displacement. In fact, this is the same as the equation for work. Since work gives you the amount of energy provided to the object, it would also give you the kinetic energy, which is going to be the force times displacement s. It says constant acceleration, the force is constant. Now, kinetic energy is in the y-axis, the displacement is in the x-axis. So if we change that in the form of y equals mx, the force would be the slope. The force is constant because the acceleration is constant. It must be a straight line. The answer should be D, like this. In question number 9, two bodies of equal mass traveling in opposite directions collide head-on. What is a possible outcome of this collision? So, first of all, if you have a collision, you know you have to use the conservation of momentum. The momentum for the first object would be, well, mass times velocity. The mass is just m. Let's use capital M in this case to not confuse it with the meters. So m and the velocity of 8. In this other case, it's a mass of m, because they're the same mass, times 4. But it's the opposite direction, so you would just use negative 4. That way, the total momentum would be just 4m. So we have to look among the answers for another answer that also has a total momentum of 4m. Option A would be 5m plus 7m. That would be 12m, not the same as 4. Option B, it's plus 1m plus 3m, and this indeed does give us 4m. The answer must be B. Let's just check C and D also. For C, it will be negative 2m plus 4m, which just would be plus 2m, which is not the same. And in D, plus 6m plus 6m, that would be 12m, which also does not match the initial condition of 4m as the total momentum. Question number 10. A driver uses the brakes on a car to descend a hill at a constant speed. What is correct about the internal energy of the brake discs? So here's the thing. The kinetic energy is constant because the speed is constant. Next, the gravitational potential energy is decreasing because it's going down. If the gravitational potential energy decreases, the energy must be going somewhere, and it's going into the thermal energy of the brakes. And of course, the thermal energy would contribute to the internal energy of the brakes. That means the internal energy has to increase, and the answer is A. if you think about it logically, thermal energy increasing would be equivalent of it getting hotter. And we know that if due to friction, things will get hotter. And then internal energy decreasing would be the equivalent of something getting colder, which is not the case. There has to be a change of internal energy because the gravitational potential energy has to be going somewhere. And that internal energy cannot be zero. Number 11, the question reads that there's two blocks, X and Y, and they're placed in contact with each other. Data for the blocks is provided. So we have initial temperatures, final temperatures, and specific heat capacities. X has a mass of m. What is the mass of y? So here's what happens. We see that the initial temperature for both of these are different. Block X starts at 20, block Y starts at 80, and they both end up at the same final temperature of 60. And what this means is block X is heating up, while block Y is cooling down. The amount of energy absorbed by X will equal to the amount of energy released by Y. We get this using mass times mass of X, which is just m, times the heat capacity of X, which is 2C, times the change in temperature, which is 40 degrees. This must equal to some mass for Y, so I'll just call this Y, times the heat capacity C, times the change in temperature, which is 20 degrees. And we keep it positive on both sides, so they're equal. That means the masses, or not the masses, the heat capacities will cancel out. And you would get m times 80, which is 2 times 40, divided by 20, which is m times 4. The answer should be C. For the next question, an ideal gas is maintained at a temperature of 100 degrees Kelvin. The variation of pressure P and the volume, or 1/8 the volume of the gas, is shown. So you have pressure, but be careful with the unit is kilopascal, so it's times 10 to the third. In the x-axis, we have 1/4 the volume, which is in per meter cubed. Okay. And the question reads, what is the quantity of the gas? Well, let's just use the ideal gas equation. PV equals nRT. And if you want the quantity of gas, notice that the units are in moles, so we're going to use N is equal to PV over RT. And we can use any of these points. We can use one point that is more convenient. We're going to use the 400 kilopascals and the 50, or 50 per cubic meter. So that would be pressure 400,000. Remember, it's kilo times 1/4 the volume. So that would be divided by 50. And divided by R, divided by T. And the question says temperature would be 100, so let's put 50 times 100 times R. Now, 400,000 divided by 5,000 gives us 80, and divided by R, the R is still there. Question number 13 is a little bit tricky. It says, a wave of period 10 milliseconds travels through a medium. The graph shows the variation of the particle displacement with distance for a wave. What is the average speed of a particle in the medium during one cycle? And what is tricky about this is it's asking for the speed of the particle, not of the wave. So if you try to use V is equal to wavelength over the period, you will not get the correct answer. The reason is this. The particle moves from +4 down to -4 and then back up again. And it says speed, not displacement. So it goes down to -4, which is 8 centimeters displacement, and then back up another 8 centimeters. So when you get the velocity as the distance traveled, you will need to use 16 centimeters. Additionally, divided by the period, how long it takes to go down 8 centimeters and up 8 centimeters, of course, that's 10 milliseconds, which would be 0.01 seconds. Let's also convert centimeters to meters, which would make it 0.16 meters. And 0.116 divided by 0.01 is just 16 meters per second. In number 14, it says, an interference pattern with minima of 0 intensity is observed between light waves. What must be true about the frequency and amplitude of the light waves? Well, according to the superpositioning principle, when you add two waves, you're adding basically the amplitudes. If there's constructive interference, they add up to 2a. But if it's destructive interference, you're subtracting one of the amplitudes from the other. And in order to get a 0 amplitude, you have to have the same amplitude for both. So the amplitude has to be the same for both in order to get a minima of 0 intensity. Second, they have to be coherent. They have to be waves of the same period and same frequency, otherwise they will not interfere. Therefore, the frequency also has to be the same. And this makes the answer C. In number 15, the question reads, a beam of unpolarized light, and I'm going to highlight this, unpolarized light, of intensity I sub 0 is incident on a polarizing filter. The polarizing filter is rotated through an angle of theta. What is the variation in the intensity I of the beam with the angle theta after passing through the polarizing filter? Now, the reason I highlighted the unpolarized light is that if it's unpolarized, changing the angle of the filter is not going to do anything. It will always be the same intensity. Unpolarized light going through a filter will always give you 1/2 of the intensity. The answer must be D. Okay, if you see A, intensity changes, it's unpolarized, it's all directions mixed in. Changing the direction of the filter will not help. It only does this if it's polarized light going through the filter. B, also not the answer. C, some of the light has to be blocked, so it cannot be the original intensity. The answer must be D. In number 16, monochromatic light of wavelength theta is incident on two slits S1 and S2, and interference patterns observed on the screen. O is equidistant from S1 and S2, so let's just mark that off. O is here. If it's equidistant, path difference is 0, so P, D equals 0, and it's constructive. A bright fringe is observed at O, yes, because it's constructive, and a dark fringe is observed at X. At X, we're going to put blue. Because it's dark fringe, that must be destructive interference. It also says there are two dark fringes between O and X. So we will also draw two more dark fringes between O and X. And because they alternate, it has to be constructive at O, destructive at the blue one, then constructive, another destructive, and then constructive. If we look at the path differences, here at O, path difference is 0. This is destructive, so the path difference is 1/2 lambda. Next constructive, which is path difference of lambda. Then destructive path difference of 3/2 lambda. Constructive path difference of 2 lambda. And finally X, path difference of 5/2 lambda. Finally, the question is, there are two dark fringes between O and X. What is the path difference between the light arriving at x from the two slits. At x, the path difference is 5/2 lambda. Your answer must be C. Number 17, a standing wave is formed on a string. P and Q are adjacent antinodes on the wave. Three statements are made by a student. 1, the distance between P and Q are half a wavelength. Number 2, P and Q have a phase difference of pi radians. And number 3, energy is transferred between P and Q. Now, one thing you should probably see is that if you have three statements, you only have these choices here. A means 3 is wrong, B is number 2 is wrong, C is number 1 is wrong, and D, nothing is wrong. So you can only have one wrong answer or 0 wrong answers. Let's look at the options. The distance between P and Q is half a wavelength. If you draw a standing wave, antinodes would be here, and that is indeed half a wavelength. So 1 checks out. Number 2, P and Q have a phase difference of pi radians. And everything in this green area and everything in this blue area will have exactly 180 degrees or pi radians phase difference, which is true. It says energy is transferred between P and Q. And energy is not transferred because only traveling waves transfer energy. A standing wave are two waves moving in opposite directions, which means the net transfer is 0. This is incorrect. So the answer must be A. Number 18. P and Q are two opposite point charges. The force F acting on P due to Q and the electric field strength E at P are shown. So they're showing you what happens at P. There is a force to the right, and then there is electric field to the left. Which diagram shows the force on Q due to P and the electric field strength at Q? So first things first. Let's look at the force. The fact that the force is pointing at Q means it's an attractive force. They have to be different charges. So whatever the charge is at P, Q must have an opposite charge because they attract. Now, second, this electric field, E, is caused by Q and is moving away from Q, which means Q must be a positive charge. And that also means E is a negative charge, which makes sense. There's a field to the left. If it were positive, the force will also be left. It's a negative charge, so the force is in the opposite direction as a field. Now finally, let's look at the field produced by P. P is a negative charge, so the field lines go towards the negative charge, which means at Q, the electric field will be to the left. And again, positive charge, field to the left, the force is to the left. If you remember, attractive forces, they should be towards each other. The answer should be B. Question 19. 3 point charges of equal magnitude are placed at the vertices of an equilateral triangle. The signs of the charges are shown. There is positive, positive, and negative. Point P here is equidistant from the vertices of the triangle, so all these distances are the same. What is the direction of the resultant electric field at P? Well, individually, this charge would create an electric field in this direction. This other charge, which is also positive, would make an electric field in this direction. But the negative charge here would make an electric field in this direction towards itself. If you add all these three arrows, adding this red arrow and this red arrow means the left and right components cancel out. It would just be downwards. The answer must be C. Question number 20. In the circuit shown, the battery has an EMF of 12 volts. Let's highlight that, 12 volts. And negligible internal resistance. 3 identical resistors are connected as shown. The resistors each have a resistance of 10 ohms. So let's write 10 ohms, 10 ohms, and 10 ohms. Resistor L is removed. What is the change in potential at X? This is a slightly tricky question. We should probably use or calculate the total resistance first. Here we have 2 parallel resistances of equal resistance, which means these two would have a resistance of 5 ohms, just exactly half of each. So we have 5 plus 5. Initially, the total resistance is 15 ohms. Now, if you remove L, the total resistance would just be series 10 plus 10, which would be 20 ohms. Okay. What about the currents then? The currents, we do not actually need the currents to get the voltages. What we do know is that initially it's 15 ohms total, right? So let's kind of replace these 2 resistors here with one resistor of 5 ohms. This is 10 ohms. And what will happen is this has 1/3 of the resistance, this has 2/3 of the resistance. So this side will have also 1/3 of the voltage, and these 10 ohms will have 2/3 of the voltage. The total voltage is 12. And that means this would have 4 volts, and this will have 8 volts. 4 is 1/3 of 12, and 8 is 2/3 of 12. So this is what happens in the beginning. Now, what happens after you remove the resistor? Well, if you remove the resistor, L does not exist anymore. It's just 10 and 10. Let's use blue for that. 10 ohms here, 10 ohms here. They both have the same resistance, which means that they have to have the same voltage as well. This would be voltage drop of 6 volts, and this would be voltage drop of 6 volts. Now, if you just do this, you might get the wrong answer because you might think, oh, well, it went from 4 volts to 6 volts, it must increase by 2, but that is incorrect. If you look at what the actual question says, is the potential at X you should be looking at, not the change in potential in the resistors. And what that means is if we draw a voltage graph, we're going to have this battery, source of EMF. We have the parallel resistors. And then we have the other series resistor. So what happens here? Initially, you start at 0 volts. It goes up to 12 volts because of the EMF. And then it drops 4 volts like this. And then it drops the 8 volts. So here's what happens. 0, 12 volts. It drops 4. Therefore, here it's 8 volts. And here is 0 volts again. At X, initially it's 8 volts. We're not talking about the change in voltage of this resistor. We're talking about the actual voltage at X. What happens after you remove L then? Well, you start at 0 volts, you go up at 12, still at 12. Then when you go through K, it goes down by 6. This is what it means. Voltage goes down by 6 to here, and then goes down here. So, starts at 0, goes to 12, drops by 6, so it goes to 6 volts here, and drops by 6 again. Which means initially X was at 8 volts, it goes down to 6 volts, it decreases by 2 volts. The answer is B. Number 21. 2 cells are connected in parallel as shown below. Each cell has an EMF of 5 volts and an internal resistance of 2 ohms. The lamp has a resistance of 4 ohms. The ammeter is ideal. What is the reading on the ammeter? Now, it's easiest to use the Kirchhoff's laws. So what we're going to do is we're going to take a path. So first, this wire has its own current, this wire has its own current, and this wire has its own current. Here, we're going to draw the direction of the currents. Let's do left because it's positive, left, and they're going to meet up here. The top green wire is going to have a current of I1, the blue wire has a current of I2, and the pink wire is going to have a current of I3. So, according to Kirchhoff's current law, we'll have I3 is equal to I1 plus I2. Okay. In order to simplify this, we also know that the top green wire and the blue wire have exactly the same things. They should be kind of symmetric. So we can say that I1 and I2 are equal, which means we can simplify this as just I3 is equal to 2I1. Okay. Now we're going to use the path. We're going to go in a counterclockwise direction, starting from here. Actually, let's start here. First step, it goes to the EMF source, which is going to be 5 volts, plus 5 volts. Next, it goes through here. The voltage drop is current times resistance, so it's I3 times 4 ohms. It goes back here. Then internal resistance, it drops I1 times internal resistance of 2. Everything goes to 0. Finally, if we use this, well, this would just be I3. 2 times I1, 2 times I1. 5 volts, I3 times 4. And you can just simplify this. I3 is equal to 1 amperes. The answer would be A. Number 22. A conductor is placed in a uniform magnetic field perpendicular to the plane of the paper. A force F acts on the conductor when there is a current in the conductor as shown. The conductor is then rotated by 30 degrees and about the axis of the magnetic field. What is the direction of the magnetic field and what is the magnitude of the force on the conductor after rotation? So first of all, we have to use the right-hand rule. You follow the current and the force, and the third part is going to be the magnetic field. So you're going to use your finger index is the current. The force, which is your thumb, is downwards. So current, thumb downwards. That means that the magnetic field has to be out of the plane of the paper, going in this third axis, out of page. Symbol for that is circle and dot. Now, if you rotate it about it, remember what the force due to current is? It's magnetic force, magnetic field, times current, times the length of the wire, times sine of the angle. And the sine of the angle is the angle between the magnetic field and the current. Rotating it like this about the axis of the magnetic field is not going to change the angle. The angle is still the same. The magnetic field is still the same, the current is the same, and the length is the same. The force will not change. So, even though you rotate it like this, the angle between the magnetic field and the current is still 90 degrees. So it's out of the plane of the page, same force. The answer is C. In number 23, a ball of mass 0.3 kilograms is attached to a light, inextensible string. It is rotated in a vertical circle. The length of the string is 0.6 meters, and the speed of rotation of the ball is 4 meters per second. What is the tension when the string is horizontal? We have a tension to the left, and we have a weight, which is a force of gravity, downwards, mg. Now, in order to make something rotate, you have to have a force towards the center in this direction. The force of gravity does not contribute to that force. What that means is the force of gravity will make it go faster or slower. This is called a tangential force. But it does not turn the direction. In order to turn the direction, you need a radial force towards the center of the circle. This actually turns the ball. And it's the force in this direction that is going to be equal to mv squared over r. The only force capable of doing this is the tension. So this is equal to the tension. Next, if you put 0.3 kilograms times 4 meters per second squared, which would be 16, divided by the radius of 0.6, this would give us the centripetal force. 0.3 over 0.6, that's of course 1/2. 1/2 of 16 is 8. The answer is B. For number 24, P and Q are two moons of equal densities orbiting a planet. The orbital radius of P is twice the orbital radius of Q. So immediately you have a planet and you have two moons at different distances. It says orbital radius of P is twice as big, so this is P and this is Q, half the distance. The volume of P is half the volume of Q. So let's draw Q bigger. The reason this is important is because if they're the same density, having twice the volume means you have twice the mass. So let's write that down. 2 times the mass of P. The force exerted by the planet on P is F. So on P, the force of gravity is G, mass of the planet, mass of P, over distance P squared. And this is simply F. What is the force exerted on the planet by Q, or by the planet on Q? So here's what happens. Q, 2 times the mass, 2 times the force. 1/2 the distance, it's 4 times the force. So the answer should be D. If you have half the distance, you have 4 times the force, and it's twice the mass, so it's twice the force as well. Number 25, a pure sample of iodine 131 decays into xenon with a half-life of 8 days. What is the ratio of the number of iodine atoms remaining over the number of xenon atoms formed after 24 days? So first, 24 is 3 times 8 days, which means it's 3 times the half-life. What that means is you're going to have the number of iodine atoms remaining equal to the initial number times 1/2 to the power of 3. Basically, you have 1/8 the initial total. And what that also means is for the number of xenon, XC is going to be 7/8 of the initial. And if you get that ratio, number of iodine atoms divided by the number of xenon atoms, you get 1/7. Number 26. The diagram shows atomic transitions E1 from here to here, E2 from here to here, and E3 from here to here. And these transitions when a particular atom changes its energy state. The wavelengths of the photons that correspond to these transitions are theta 1 or lambda 1, lambda 2, actually that was blue, and lambda 3. What is correct about these wavelengths? And it has equations for the wavelengths. So first of all, since these are energy levels, the energy of E1 is going to equal to E2 plus E3. So let's write that down. E1 is equal to the energy E2 plus the energy E3. Now, photon energies are Planck's constant times the frequency. But remember, you need to use wavelengths, so it's going to be speed of light over the wavelength. And since this is for the first transition, E1, I'm going to use lambda 1. So hc over lambda 2 plus hc over lambda 3. Well, all of these are the same. Just 1 over the wavelength of the photon released in the first transition, 1 over the wavelength of the photon released by the second transition, plus 1 over the wavelength of the photon released in the third transition. The answer must be D. In number 27, carbon C12 and hydrogen H1 undergo nuclear fusion to form nitrogen. What is the number of neutrons and number of nucleons in the nitrogen nuclide? So if you look at the reaction, we have carbon 12, we have hydrogen 1 becoming nitrogen, and a photon. Well, the photon has no charge, no mass, so it doesn't really matter. What's going to happen is you have to conserve the number of baryons, so it's 12 plus 1. You're going to have 13 nucleons for nitrogen, and you have to conserve the charge. 6 plus 1 has to be 7. 13 nucleons, 7 positive charges, which means their number of protons is 7. The other 6 must be neutrons. So, number of neutrons is 6, number of nucleons is 13. The answer is B. In number 28, wind of speed V flows through a wind generator. The wind speed drops to V over 3. After passing the blades, what is the maximum possible efficiency of the generator? So, number 1, if you look at the physics booklets, you'll see there is an equation for the theoretical maximum kinetic energy of the wind. So, the maximum theoretical kinetic energy, or power, of the wind is 1/2 times the density of the air times the cross-sectional area times the velocity to the third power. And this is the initial. Recall that after passing, it's 1/3 the velocity. So it would be 1/2 times the density, same area, 1 over 3 V cubed. If we just color code this as 1/3 here, cubing it would give you 1 over 27. Everything else is the same. This is the same as the original. So you started with, let's say, 27 over 27 of this original, and you're left with 1 over 27 kinetic energy, which means the other 26 over 27 would have been absorbed or used by the blades of the windmill, which is the theoretical maximum? The answer would be D. Number 29. The diagram shows for a region on the Earth's surface the incident, radiated, and reflected intensities of the solar radiation. What is the albedo for the region? Albedo only considers the reflected amount of energy or intensity and the incident intensity, and is defined as being equal to the reflected over the incident, which would be 150 divided by 600, which is exactly 1/4. The answer is A. Question 30. Light of wavelength lambda is diffracted after passing through a very narrow single slit of width x. The intensity of the central maximum of the diffracted light is I sub 0. The slit width is doubled. What is the intensity of the central maximum and the angular position of the first minimum? So first things first. If you double the slit width, you should get approximately twice the amount of energy through the slit. The intensity would probably double. You only get 4 times intensity if you have 2 slits and constructive interference. So next, what happens if you make the slit wider? Well, the angle to the first minimum is the wavelength over the slit size b. In this case, instead of using b, they use x. Doubling it will make the slit size or the angle 1/2 the size. So the angular position of the first minimum is going to be here. The answer is B. Number 31, an observer with an eye of pupil diameter D views the headlights of a car that emits light of wavelength lambda. The distance between the headlights is L. What is the greatest distance between the observer and the car at which the images of the headlights will be resolved by the observer's eye? So first, this is resolution, of course. It's a pupil, so it's circular aperture, not slits. What you have to do is you have to use the Rayleigh criterion, which is the angular separation between the 2 points of light has to be greater than or equal to 1.22 times the angle to the first minimum. First, how do you get the angle to the first minimum? You have to use the wavelength divided by b, the diameter of the circular aperture. But in this particular question, they used the letter D instead, so we changed that to D. And highlight it as so. Next, it's the minimum distance, so that's when it's equal to each other. And finally, well, usually if you have the angular separation, you have a distance D, and this is separation S. But in this case, they use the letter L for the separation between the points of light. It's highlighted as in green, like so, lowercase or capital L. Next, the distance. This is the distance that we have to find. So it's highlighted in yellow. And let's call this X. So it will be L over X. This is the small angle approximation for this arc. Highlight this in green, highlight this in yellow. We're trying to find X, so X is equal to, well, L times D over 1.22 times the wavelength. The answer should be C. In number 32, a charged sphere in a gravitational field is initially stationary between two parallel metal plates. There is a potential difference V between the plates. 3 changes can be made. 1, you can increase the separation between the plates. 2, you can increase the voltage between the plates. And 3, you can apply a magnetic field into the plane of the paper. What changes made separately will cause the charged sphere to accelerate? So, number 1, initially stationary. This means net force is 0. You have the force of gravity going down. You have to cancel that out. We have to have an electric force upwards. This electric force is caused by the charges of the metal plates. Now, this electric force, of course, is equal to the charge of the sphere times the electric field. So 1, if you increase the separation, electric field is the voltage difference divided by the distance between the plates. Increasing the separation would make the electric field weaker, which means this force becomes smaller and it will start dropping. So it will cause it to accelerate. Good. 2, if you increase the voltage, you make the electric field stronger. The electric force will become stronger and will accelerate upwards. So this also makes it accelerate. But 3, applying a magnetic field, the magnetic force on the charge is the charge times the velocity times the magnetic field strength. The velocity is 0 initially, therefore this will not accelerate just because you put a magnetic field. Number 3 does not make it accelerate. So the answer should be A. Number 33, an object of mass lowercase m is launched from the surface of the Earth. The Earth has a mass of capital M and radius r. The acceleration due to gravity at the surface of the Earth is g, lowercase. What is the escape speed of the object from the surface of the Earth? Well, if you look at the physics booklet in chapter 10, it does give you an equation for the escape velocity. Escape velocity is the square root of 2gm over r. And the reason it's 2gm over r is because the kinetic energy, if you want to escape, has to be equal to the gravitational potential energy. So 1/2 mv squared is equal to gravitational constant, mass of the planet, mass of the object, over the distance. And this gives you this equation. But notice here, they don't use the gravitational constant, which means that you have to use the gravitational field strength. So let's get the equation for the gravitational field strength. The gravitational field strength, one second, is gravitational constant times the mass of the planet divided by the distance squared. And we have to find a way to substitute this in here. And there's lots of ways to do it. You can either use the mass equals to something and substitute it. What we're going to do here, though, is just multiply it by r. G, gravitational field strength, times r is equal to gravitational constant times the mass of the planet divided by the radius. Because it's radius squared times r, of course. This squared cancels out. And this is exactly what we have in our equation here. Which means if we substitute this with g times r, you get the square root of 2, the gravitational field strength times r. The answer is B. In number 34, the graph shows the variation of the magnetic flux in a coil with time t. What represents the variation with time of the induced EMF across the coil? And we have to start with Faraday's law. Faraday's law says the EMF is negative N delta flux over delta T, which you would say as the rate of change of magnetic flux linkage. First, it's just one coil, so N is equal to 1, which is not really important right now. What is important is, if you see this, the rate of change of flux, which is delta phi over delta T, is a slope of this graph, because you have time in the x-axis and flux phi in the y-axis. So this graph for EMF has to be the slope of this graph, but flipped with a negative sign on top. So this graph has 0 slope at the beginning, which is what we see in option A and option B. C and D do not have 0 slopes at the beginning. They have some value, which means they cannot be the answers. Next, the slope goes down, which means it's a negative slope. But remember, the equation for Faraday's law has a negative sign as well, which means it will be a positive value. The answer is A. Number 35, a direct current I in a lamp dissipates power P. What root mean square value of an alternating current dissipates the average power P through the same lamp? This is a trick question, and the reason it's a trick question is because the root mean squared of an alternating current literally means what equivalent direct current do you need to get the same average power. So if you need a power I in that direct current, the RMS would also be I. The answer will be C. Number 36, the arrangement shows 4 diodes connected to an alternating current AC supply. The output is connected to an external circuit. So here, you can think of these 2 points as being the plugs, right? Now, if you've done the class, you'd know there's a very simple way to know what the direction of the diode should be. All the diodes should be pointing towards one side, and that side is where the current goes out. So let's say, if you say all the current should go out here, that means it should go down here, and all these arrows should be pointing to this corner of the diamond. These 2 are correct, but this one is not pointing in the right direction. If you want this side to be the output, you have to put these diodes in the opposite directions. So what happens if you do it like this instead? Well, let's say you put a positive side here. The voltage in current will go this direction. It gets blocked here. It goes through here. But notice it is not forced to go into the output. It can just go directly to the other side. It skips the output. Basically, it short circuits. When it does this, it's the same thing as if you had a battery and 2 pathways, one with a resistor and one without the resistor. If you don't have a resistor here, 100% of the current will just go through here. The voltage across the resistor will be 0, so therefore, across the output, you have 0 current. All the current would directly go to the other side, and you'd probably burn your house. Number 37, you have 3 identical capacitors and they're connected as shown below. What is the order of increasing total capacitance for these arrangements? So we kind of have to calculate the capacitance for all these things. Number 1, if they're in series, 1 over the total capacitance is equal to 1 over capacitance 1 plus 1 over capacitance 2 plus so on and so forth, 1 over capacitance n. If they're parallel, it's just a sum. Total capacitance is equal to capacitance 1 plus capacitance 2 plus capacitance 3, and so on. So let's look at the first one. These 3 capacitors are C, C, and C. They're in series. That means it has to be low capacitance. If you use this equation, you just get total capacitance is equal to 1/3 C. What about Q? These are all in parallel. Just add them up. C to C, total capacitance is equal to 3C. Now it's R and S that are a little bit more difficult. If you do, let's do the parallels first. Here, this would be parallel. So this would be 2C, and this is 1C. So let's replace this with one capacitor here. And let's actually do this equation. 1 over total capacitance is equal to 1 over 2C plus 1 over C, which is equal to 3 over 2C. And you have to flip it over again. Means the total capacitance here is equal to 2/3 C, slightly below 1. Finally, let's use this a different color. These two in series will give you 1/2 capacitance. And they're parallel with just one other capacitor, which is just C. You add them together, the total capacitance should be 3 over 2. So 1.5 C. In order of increasing, we have the smallest one first. Smallest one is P. Second one would be 2 over 3, which is R. So it's going to be A. Third one would be S, because it's 1.5, S. Last one is Q, which is the largest, Q. The answer is C. Number 38. Light with photons of energy 8 times 10 to the negative 20 joules are incident on the metal surface in a photoelectric experiment. The work function of the metal surface is 4.8 times 10 to the negative 20. What is the minimum voltage required for the ammeter reading to fall to 0? Okay, so the photon energy, so let's go E, energy of the photon. This is the total energy that can be given to the electron and gets divided into two things. It can become the kinetic energy, and some of it is used as energy required for the electron to escape, which is the work function. The work function is 4.8 times 10 to the negative 20 joules. The photon energy is given as 8 times 10 to the negative 20 joules, which means the kinetic energy of the electrons, or the maximum kinetic energy, is 3.2 times 10 to the negative 20. And the way you calculate this is the charge of the electron times the voltage used to stop it. This is the stopping voltage, the voltage that you're required to find. The charge of the electron is 1.6 times 10 to the negative 19. So if you do 3.2 times 10 to the negative 20 divided by 1.6, you get, of course, 2. But then this is negative 20, negative 19, to the power of negative 1. So the answer is A, 0.2 volts. In number 39, it says, what is the evidence for wave-particle duality? Going through all the options, the line spectra of the elements gives or proves the energy levels. Otherwise, it also proves that the energy levels are discrete for the electrons that are surrounding an atom or surrounding the nucleus. B, electron diffraction. Diffraction only happens with waves, but electrons are particles, so it has particle for electron, and it's doing something only waves do, so the answer should be B. C, the Rutherford alpha scattering experiments are the ones that uncovered or proved that the nucleus exists in its very high density and positive charge. So this is not about wave-particle duality. And D, the gamma ray spectrum is caused by the energy levels of the nucleus. Question number 40, which is also the last question, says the decay constant gamma of a radioactive sample can be defined as something. So let's get the decay constant first. The most simple equation you get is the activity being equal to the decay constant times the number of particles. And we know the definition of activity is delta n over delta t. Delta n is the number of atoms that decayed. Delta t is, of course, the amount of time it takes for them to decay. This is the rate of decay. And we can put a negative in front of the delta n because, of course, final minus initial is always a negative number. So let's look at A. A, the number of disintegrations, it would be just n. And if you want to get the definition of this, the decay constant is delta n over n and delta t. So if you just have the number of disintegrations, actually this would be delta n. It does not fit the definition here. It cannot be A. B, the number of disintegrations per unit time. So B would be delta n over delta t. We're close. It's this part of the equation, but it does not have this, so it cannot be B either. For C, the probability that a nucleus decays in a radioactive sample. This probability is equal to how many decayed divided by the original number. This is lacking the delta t, it cannot be C. And D, the probability per unit time. So it's probability delta n over n divided by unit time, delta t, and it's exactly what we want. The answer is D. Well, that is all for today. Thank you for watching and see you next time.